The name of the problem is inclined plane in elevator. The setup is as follows. We have an elevator. Okay, we have inside an inclined plane with an angle theta. I have a mass m sitting on the inclined plane, which is tied to the wall with a string. Now, of course, the string has a tension T, which holds the mass in place. And the trick is that the elevator is accelerating upwards with acceleration A. So now, of course, there is gravity down. We're supposed to find the tension in the rope. Now, there are two ways to do this. One is actually thinking within the accelerating frame of the elevator. In this case, we will use a ghost force, which is totally fine if you know what you're doing. And in the second case, we can just do it using just a free body diagram, thinking in the inertial frame with no ghost forces, just considering that the mass itself will be accelerating up with acceleration A. So the ghost force approach gives the faster answer. So if I go to in the accelerating frame of the elevator, if I draw the free body diagram, so since it's accelerating up, there is going to be a force, a ghost force pointing down opposite the acceleration, which is going to be of magnitude capital M times G. And there is also, the ghost force is capital M times A, the acceleration. There's also going to be the additional force of gravity, which is parallel to this, which is going to be M, again, capital M times G. Now, what other force is there on the object? There is if this is the vertical, the horizontal, there is going to be the normal force, which is just the force applied by the inclined plane on the mass. And there is going to be the tension of the rope, which is going to be in that direction. Now, this angle is going to be theta, and that angle is going to be theta. Now, I need to write two equations. So I can do it two ways. One is, well, I can do it a lot of ways. I need to choose my x and y axes. On which axes am I going to project the forces and write down my equations is the question. So one good choice for this is choosing this as my x direction and this as my y direction. Now, in this x direction, what is my equation? Now, if that angle is theta, this angle is theta, so this is, in fact, pi over 2 minus theta, this one. So I'll need to split this into its components. So in fact, in order to find the tension in the rope, I only need one equation. Let me write the equation along the x-axis, and we'll see what happens. So if I take my positive direction to be that, I have T. Now, in this direction, I have the projection of both of these forces, MA and MG, and it's in the opposite direction. So I have a minus ma plus mg times I have sine theta equals 0. It's 0 because in this accelerating frame, which I use the ghost force, the mass is just stationary. Now, from this equation, t just drops out as t equals m a plus g sine theta. Now, if I write the other equation, which will turn out to be n minus, in the opposite direction, I have m a plus g cosine theta, right, equals 0. This just gives me n equals m a plus g cosine theta. Since we're not really interested in n, the second equation was not of much use towards the answer. So I find this. Does it make sense? Well, it does make sense because, well, if the elevator is accelerating upwards, it's going to be pressing me down on the floor. So it's going to be increasing the effect of gravity. So it makes sense that A itself will be added on top of G in this case. Now, sine theta, does that make sense? If theta is 0, which means the plane is horizontal, then sine theta will be 0, and the tension will be just 0, because the rope, you don't need the rope to keep the mass in place in that case. So this is solving it in the accelerating frame. I could do it in the inertial frame without using ghost forces. To do that, in this case, well, the free body diagram looks like this. So I have just mg acting down, and this is the vertical and horizontal. I have the tension in the rope with angle theta, and then I have the normal force N, and this angle is also theta. Now, in this case, of course, the whole system is accelerating up with acceleration A. So if I go about writing the equations in this case, what do I get? Now, again, I can choose, well, my axes. In this case, I'll do the normal x and y axes just to show how things change when you're not lucky with your choice of axes, or careful for that sense. OK, so if I write it according to the regular x and y, I have towards the right, I have t cosine theta, right? And here towards the left, I have minus n sine theta. Now, there is no horizontal acceleration, so I end up with equals to 0. Now, in the y direction, I have t sine theta, positive, and then I have plus n cosine theta, again positive, and then I have minus mg equals, there's acceleration in the y direction, which is a, so this must be mass times a. Now, if I take the second equation and arrange it just a little bit, I get t sine theta plus n cosine theta equals m g plus a. Again, the g and a got added together, so I'm happy with that. Now, I need to eliminate n from this equation because I'm interested in t. So from that equation, I can find that n equals t cos theta over sine theta. Is that right? N equals, yes, t cos theta over sine theta. Right. So I can substitute that n over here. So I get t sine theta plus, so n is t cos squared theta over sine theta equals m g plus a. Now, I don't like the sine theta in the denominator. If I multiply through with sine theta, which I can do simply like this, so this becomes sine squared theta, and I get a sine theta on the right there. So I have t sine squared plus cosine squared is just 1. So this reduces to t equals m g plus a sine theta, which yields the exact same result as the one which we did with using a ghost force. Are the units correct? Well, the tension is a force, so it's just mass times acceleration. Sine theta is unitless, so we are fine. So we found the same answer in both ways. Yeah, that's the solution to our problem.